This video is on similar triangles. Similar triangles have the same shape but are not necessarily the same size. This is different from congruent triangles, which have the same shape and the same size. So for example, the two triangles below are both equilateral triangles, so they have the same shape, that is 3 60-degree angles and 3 congruent sides. But they do not have the same size because their side lengths are different. So these two triangles are not congruent, but rather are similar to each other. In general, two shapes are similar if all of their corresponding angles are congruent and all of their corresponding sides are proportional. So for example, in the diagram below, quadrilateral ABCD is similar to quadrilateral WXYZ. Notice that this little squiggly symbol means is similar to. We know this is true because angle A is congruent to angle W, angle B is congruent to angle X, angle C is congruent to angle Y, and angle D is congruent to angle Z. And the ratios of their sides are also equal. So the length of AB over the length of WX is equal to the length of BC over the length of XY, which is equal to the length of CD over the length of YZ, which is equal to the length of DA over the length of ZW. Notice that if we substitute in the actual side lengths into this proportion, then we have 15 over 5, which equals 12 over 4, which equals 21 over 7, which equals 8 over 16, all of which equal 3. Recall that a ratio is a comparison of two numbers by division. So for example, 3/4, 4 to 3, written here with a colon, and written with words 4 to 3, are all considered ratios because you're comparing those two numbers by division. A proportion is an equation that states that two ratios are equal to each other. So for example, 4/3 equals 8/6 is a proportion because it says this ratio is equal to this ratio. Going back to our quadrilaterals, we can say that the scale factor of quadrilateral ABCD to quadrilateral WXYZ is 3 to 1. We got that number from this ratio here. In other words, quadrilateral ABCD is 3 times larger than quadrilateral WXYZ. Quadrilateral ABCD is an enlargement of quadrilateral WXYZ by a factor of 3. So we can also go the other direction and we can say that the smaller quadrilateral WXYZ to quadrilateral ABCD, that scale factor is 1/3 or 1 to 3. That is, quadrilateral WXYZ is 1/3 of the size of quadrilateral ABCD. That is, quadrilateral WXYZ is a reduction of quadrilateral ABCD by a factor of 3. With regard to triangles, we do not need to show that all the angles are congruent and that all the sides are proportional. As with triangle congruency, as we saw in topic 4, there are some shortcuts. The first one is the AA similarity. It says that if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So if angle A is congruent to angle X and angle C is congruent to angle Z, then triangle ABC is similar to triangle XYZ. SSS similarity is side, 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 and that says that if the lengths of three sides of one triangle are proportional to the lengths of the corresponding three sides of another triangle, then the triangles are similar. So if AB divided by XY is equal to BC over YZ, which is equal to AC over XZ, notice those are the corresponding sides shown here in color, then triangle ABC is similar to triangle XYZ. And our last one is an SAS similarity, side angle side, and it says that if the lengths of two sides of one triangle are proportional to the lengths of the corresponding two sides of another triangle, and that their included angles are congruent, then we can say the triangles are similar. So if AB over XY is equal to AC over XZ, and angle A is congruent to angle X, notice those are the included angles between the two sides mentioned, then we can say the triangle ABC is similar to triangle triangle XYZ. So let's take a look at a couple examples here. Oops. So for the first one here, we're told that triangle ABC is similar to triangle HGF, and we need to find BC. So if I know that ABC is similar to HGF, I know that AB over HG is going to be equal to BC over GF, which is going to be equal to AC over HF. Now it might get a little confusing looking at the triangles, but you can always work off of the similarity statement because they have to be in that particular order. Angle A has to be congruent to angle H, and the ratio of AB over HF has to be the same as the ratio of BC over GF. So sometimes just looking at the letters can be a little bit easier. So what is it we're trying to find? We're trying to find BC, so I have to use that ratio there. And I can use either one of the others. So I think I'll use the first one. So AB is 72, and HG is 12, and that's equal to BC over GF, which is 8. And doing some cross multiplying here, 12 times BC is equal to 576. So BC is equal to 48. Here's a couple more examples. This says the two triangles below are similar. We need to find the length of PW and write a similarity statement. So I'm going to actually do that backwards, and I'm going to write my similarity statement first. Notice that it looks like one triangle, but we have another triangle right inside of there. Notice that angle P is actually a part of both triangles. So I can actually name my triangles here. I can name this angle PVW, triangle PVW is going to be similar to, and now I have to kind of do the same thing with the large triangle, PQR. Okay, and notice that what I don't know is kind of this longer piece here of PW, of the smaller triangle, which is what I need to find. So I'm going to write a proportion that says PV over PQ. So that's the shorter top side of the smaller one over the longer top side of the bigger one, is equal to PW over PR. I can also confirm this by looking at my similarity statement. The first two letters over the first two letters equals the first and last over the first and last. And indeed that does work. So now I can plug in numbers. So PV is 9. PQ, be careful, is 18, and that's equal to PW, which I need to find, over 22. So doing cross products, 18 PW equals 198, and dividing both sides by 18, PW is equal to 11. And actually the reason I knew that they were similar because I had a side, an angle, and a side. So if they ever ask you why, you can say side angle side similarity is my reason there. And our last example is similar to this. This says the two triangles below are similar. Find X and write a similarity statement. Actually, this problem bothers me a little bit because both triangles have an angle U, which normally that isn't the case. So let's go ahead and write a similarity statement. Notice that I have two sides called out and then I have an angle in between. So I'm going to go with UVW is similar to UST. Oops. Okay. And I need to find X, which is UV, so I think I will do a ratio that says UV over, and that corresponds to US in the other triangle, equals VW over ST. Now, plugging in numbers, UV is 5x plus 11, US is 18, and VW is 88, over 24. Now, solving that with cross products, that's going to give me 120x plus 264 is equal to 1,584. And subtracting 264 on both sides gives me 120x is equal to 1320, or x is equal to 11. So in this video we took a look at similar triangles, and in fact a larger picture, similar polygons, where we have to show that all corresponding angles are congruent to each other and all corresponding sides are proportional. However, when we're dealing with triangles, we can use shortcuts. We can use an AA shortcut, SSS shortcut, or an SSS shortcut to show similarities between two triangles.